Hello and welcome to the AP Physics 1 screencast for the first section of energy. My last one went a little long, so I'm going to try to tighten it up a little bit. Make sure that you don't have like 25 minutes worth of video to watch. So let's just get started. Here's where you can find all of your materials for this under Work, Energy, and Power. We are looking at O1 energy conservation right here. And before we get into this, I want you to watch this Bozeman video right here, kinetic and potential energy. So go ahead and watch that. And once you do, come back to the video, give it a pause. Okay, hopefully you have watched that. I'm going to be showing you a PHET sim. You know, I love these. This is one of my favorite ones, Energy Skate Park Sim. This is really fun. I think you guys are going to enjoy it. But let's go right into the notes here. Well, first of all, let me show you where your formulas for this energy unit can be found on the AP Physics 1 equation sheet. I've got right here, just to kind of scroll up a little bit. This area right here is where you're going to find these, as well as right here. So just to kind of give you that kind of information there. All right, so I'm going to go ahead and get started in here. Okay, energy, work, and power. And conservation. You're going to see that word conservation a lot, pretty much the rest of the course. That's going to be a theme in a lot of the units that we cover. Remember, we're going through rotation, so we're still leaving. We're not going to do electricity and waves due to our shortened test period, but conservation is a theme that kind of runs throughout the rest of this. So we are going to first look at energy, kinetic and potential energy, types of energy, and also we'll start looking at this idea of conservation of energy, what that really means. And then get into work and how energy and work are related very closely. And springs, we'll take a little bit from simple harmonic motion that we did earlier and bring that into that. And then finally power. Now, right there it mentions machines and efficiency. I need to take that off actually. That is something that we are not going to look at. It's not covered on the AP exam anymore. I've skipped it for pretty much most of the time I've been doing this. On the stuff that you have for this course, just ignore machines and efficiency. All right, this first part is just defining what we mean by kinetic and potential energy. And then we're also going to do the second part there, looking at actual formulas for kinetic energy and gravitational potential energy, and kind of learning how to use that in terms of solving problems, things like that. Do you have any energy today? That's always the question, right? This is always fun to ask, you know, first block on a Monday morning. No, we don't. Leave us alone. So yeah, this is always relative, but it's a good opener here. What is energy then? You know, okay, when we say, okay, I don't have a whole lot of energy. You know, I've always told you there's terms that we look at in physics that mean one thing in the real world and one thing in our physics world. This unit is full of those. So what is energy? Well, we need to find out. Okay, energy is the ability to do work. Okay, great. What's work then? Well, we're going to find that out. But there's two things that are involved with this whole idea of work. It involves a force, and that force is acting over a certain distance. So it requires both a force and for something to move a certain distance. That's going to be really key once we get into work. And no, this isn't really a strict definition for work. There's a few qualifiers that we'll get into a little bit later too. Okay, the joule, that is the SI unit for measuring energy or work. Where we get this from, this is basically, just as it mentions there, how much energy it takes to exert 1 Newton of force over a distance of 1 meter. You can maybe already see this relationship between energy and work because, well, that's kind of how we just define work, right? But a joule, and by the way, that is named after the famous scientist and physicist James Prescott Joule, I think is his name. He is famous for work with looking, kind of laying the foundation for the whole conservation of energy. And also, if I recall correctly, he worked with how heat energy is related to mechanical energy as well. So, you know you've done well if you have a physics unit named after you. So he did well. So yeah, 1 joule is 1 Newton times 1 meter. So you could also rephrase it as a Newton meter. Or if you go back to F equals ma and just substitute that in for Newton, well, you also get kilograms meter squared over second squared. But I'm just going to use joule, and I think you will as well. So what are some other units for measuring energy? Well, we have a calorie, which is approximately 4.19 joules, and then we have a calorie, which is approximately 4,190 joules. Okay, what's the difference here? Okay, one obviously has a capital letter there, but the reason why we have a capital C instead of just calling it a kilocalorie is that, oddly enough, this, if you've paid attention to food labels, this is a food calorie. Actually, it is officially a kilocalorie, but who wants to write kilocalorie on a box? You just want to write calorie. So we just kind of designate that by the capital C. So 1 calorie of food is going to be approximately equal to a little over 4,000 joules of energy. Sounds like a lot, right? And then also a BTU, and that stands for British Thermal Unit. That's kind of the equivalent of like inches to centimeters, that type of thing, where this is not a metric version. And a BTU, I looked this up too, it's basically the amount of energy it takes to, or the amount of heat that it takes to raise 1 pound of water by 1 degree Fahrenheit. So that's the definition of a BTU. Of course, we don't use that. All right, 2 types of energy here. Let's look at what we got here. We have a picture of a wind farm, and then what looks like a dam somewhere. So the wind farm is kind of our designation for kinetic energy, while the dam is for potential energy. Think about, okay, why would that be? Well, it all has to do with where is the energy coming from? Well, with kinetic energy, that energy is due to motion. Think back to our first unit, kinematics. Kinematics was motion, right? The study of motion. Well, kinetic, that's that same root word there. Kinetic is just motion. Potential energy is a little more complicated. It's either due to position or arrangement of some object or whatever, and it's associated with a particular force. For our purposes, that is mostly going to be gravity. Oh, yes, you do have to memorize. No, of course you don't. This is just showing you some of the input and output. All of these are inputs into our energy system. You can see a lot of that is obviously made up of fossil fuels, and so that kind of makes up our supply. So this is in quadrillion BTUs as of 2007. Then we export a little bit, and then the rest of this kind of goes out to various, residential, commercial, industrial. So this is just kind of a neat way of showing kind of how energy flows throughout our system here. I'm going to kind of go through these really quick. Mechanical, kinetic, so this is just types of energy, examples of that, whether it's kinetic or potential. What's it due to? In other words, what is kind of the source of this? And then how is that work done? So for mechanical kinetic energy, look at a wind farm, and obviously that is a kinetic type of energy. But what does that do to? Well, you might be tempted to think, well, it's the blades moving around. Think, what's the source though? What is actually causing the blades to move? Well, it's the motion of the air molecules. And then it's that motion of the air molecules that pushes on the blade, which turns the turbine, which generates the electricity. And then for gravitational potential energy, like a hydroelectric dam, that is obviously potential energy. So what does that energy do to? Well, that is the elevated position of the water, because as the water is elevated, then that means gravity can actually do work on that. And as it does that, it exerts a force on the turbine, generating the electricity. And then chemical energy. We won't look at this so much as far as what we're doing for calculations, but it's good to know anyway. So a lot of that can come in like fossil fuels. So, if you're driving, you're going to put gas in your car. Well, what's happening with the gas? Okay, that's potential energy. What does that energy do to? Well, it's the arrangement and positions of atoms in molecules. In other words, just kind of the molecular structure there. And, gas in a car, when you apply heat there, that heat is going to break those chemical bonds. When it breaks those chemical bonds, it releases heat, and that can cause motion. Moving on, nuclear energy is kind of similar there. That is also potential, and that is also due to the position arrangement of the subatomic particles in this case. And then how does that do the work? Well, the fission process is causing that. Basically, in a nuclear power plant, you're going to have this kind of a similar thing where it's going to heat the water, and then the water is going to turn to steam. The steam is going to turn the turbine. That's what happens a lot of times. So thermal energy, that is kinetic. That's basically the heat coming from the ground. That's the random motion of molecules, and once again, using that heat to generate steam and turn turbines. You kind of sense a pattern here. The last one, a clock spring. What type of energy do you think that would be? That's going to be elastic potential energy, if you think back to simple harmonic motion. So elastic potential, that means potential, obviously. What does that energy do to? Well, if you think about stretching out a slinky, the farther you stretch it, the more energy you get. So that just you're stressing that slinky. It's wanting to go back to equilibrium there. And then that's going to exert a force, moving apart in a clock, maybe. Okay, moving along. I want to get this under 15 minutes here. Mechanical kinetic energy is defined by classic physics formula here, 1/2 mv squared, where m is mass, v is speed. Okay, if you take a quick look at this, which of these variables, if you were to say double them, which one would have more of an effect there? Well, obviously that's going to be speed, because if you double the mass, you double the kinetic energy. If you double the speed, then that speed is squared, meaning you actually quadruple your kinetic energy. So good thing to remember about this formula. Gravitational potential energy. So we're thinking about this near the Earth's surface. In other words, in this case, G is going to be 9.8 for the most part. And then we have mass, and we also have height above a reference. Okay, what do we mean by a reference? Well, H is pretty well arbitrary. H is just what you make of it. And imagine this. Okay, say I'm standing next to a table that's 3 foot high relative to the floor. And I have in my hand a ball, and I'm holding that ball up 6 feet high relative to the floor. Well, if I drop that ball next to the table, that ball is going to fall 6 feet. So H should be 6 feet in this case. But if I turn my arm around and I'm holding that ball over the table and I drop the ball and it drops on the table, well, I've just changed my H. My H is now 3 feet because it fell onto the 3 foot high table. So that's why we say H is arbitrary in this case. And so the potential energy is all relative to what that H is. Now, mass and G are always going to be positive, but H actually can be negative in some circumstances. I mean, imagine if I were to kind of bend down and hold that ball at 2 feet above the floor. Well, in that case, it had, relative to the floor, it has potential energy, but relative to that table, it would have no potential energy because there's just nothing there. H is, below zero there. Conservation, as we said. Conservation laws just mean that whatever you start with is what you finish with, to be very brief. Certain things can either be created nor destroyed. Matter, for instance. Matter is not created, matter is not destroyed. It's a fixed amount that's not going to change. So some other aspects of the universe that are conserved, you have matter, mass, energy, which we're going to look at here in a little bit, charge, like electric charge, spin, and momentum, which is our next unit. Okay, very quickly, I'm almost out of time here. So energy can either be transferred or transformed. Transferred just means, kind of like I'm going to go to a sim really quick here. If you think of like a Newton's cradle, like this, that energy is being transformed between those balls as they're moving there. Also, it can be transformed, like from kinetic to potential. And then you see the, E equals mc squared is kind of your notable exception there. Just kind of take a look at these really quick. Sorry, I need to get under 15 minutes. And then all this is saying here is we can take Ke1 plus Pe1 equals Ke2 plus Pe2. Just means that energy before equals energy after.